Okay, good morning everyone. So, I think everyone has joined today's class. Okay. Okay, let me share one screen that I have discussed in last class. Okay. So last class we have discussed about velocity distribution through laminar flow between two parallel plates, and then we have again derived one equation for maximum velocity and average velocity, and after that we have find out the ratios of maximum velocity to average velocities, and after that we have some doubts. So let's start today's class from this topic: drop of pressure head for a given length. Okay, so I think everybody is familiar with the term pressure head, isn't it? So as you know, pressure head is that height of a liquid that corresponds to a particular pressure exerted by the fluid column on the base of its container. It may also be called static pressure head or simply static head. Okay. In Bernoulli's theorem, I think you have got the pressure head, isn't it? So here we have to find out that pressure head, okay, for a given length. So how can you find out? My slide is visible to you. Okay. If you find any problem, please let me know, okay? So pressure head you know already, and yes, we have in last class we have got average velocities expression, isn't it? So that is u bar equal to minus 1 by 12 del mu del p by del x t square. Okay, so from this equation, if you find del p by del x, then it will be minus 12 mu u bar t square. Yes, the pressure head formula, the head h is given by p by rho z, where p is the pressure exerted on the fluid and rho is the weight of the fluid. So head is p by rho z. Okay, rho is the density of the fluid and z is the acceleration due to gravity. Okay, so you know these terms already. So this h we have to find out here. Here we have taken two cross sections, isn't it? 1 and 2. Let's distance between the two cross section is L, and L is given by x2 minus x1. From the figure you can find out L value equal to x2 minus x1. P1 is the pressure exerted on the cross section 1, and P2 is the pressure exerted on the cross section 2. So in between these two cross section we have to find out the drop of pressure. Okay, drop of pressure we find out because in every pipe flow or in every liquid system there is a drop of pressure. Okay, so there is a height difference between the heads of fluid. So we have taken this to cross section. x2 is the distance from the starting point, so L equal to x2 minus x1. So from this average velocities equation you have to find out the pressure head. How can you find out the pressure head? You have got the term del P by del X. Now this del P by del X you have to integrate with respect to x direction. Okay, so if you integrate this equation you have to consider a limit from 1 to 2, or you can take 2 to 1. Okay, we are measuring the heads with pressure drop between the two cross section, that is not for the whole pipe flow, only to cross section. So we have taken this limit as 2 to 1. Okay, after that you have to integrate del P by del X. So if you take only del P term, the equation will be del P equal to minus 12 mu u bar divided by t square into del X. Okay, so integrate both sides from 2 to 1, then you will find this del X change in length. Del X will be x2 minus x1, which is equal to L. Okay, so you put the values. After integration, what you have got, try to solve yourself. You have to find out P1 minus P2, that is pressure exerted on cross section 1 and pressure the difference between these two, pressure exerted on the wall 1 and pressure exerted on the wall 2 on the cross section 2. So P1 minus P2 will be how much? Solve yourself. Yes, so P1 minus P2 will be how much? Yes, 12 mu U bar L divided by T square. L is the distance of between the cross section where we have find out this pressure difference, and U bar is the average velocity, mu is the viscosity, T is the difference between the two fixed parallel plates. So, as I have told you, head is given by P by rho Z, isn't it? So, you divided this both side by rho Z. So, it will be how much? P1 minus P2 divided by rho Z equal to 12 mu U bar L divided by T square rho Z. Okay, that means if HF is the drop in pressure head, then your equation will be HF equal to P1 minus P2 divided by rho Z equal to 12 mu U bar L divided by rho Z. Okay, is that clear to you? Have you understood how we have calculated drop of pressure head? HF, yes. From this head equation only, you should clear this head equation, H equal to P by rho Z for a static head. Mark this equation as equation number 7. Okay. Mark it as equation 7. So till now we have got 7 equations. Okay. Okay. Let's move to the next slide. It is all about shear stress distribution. How shear stress is distributed throughout the fluid flow. Okay. Yes, from Newton's law of viscosity, all of you know that shear stress tau is equal to mu to del u by del y. Okay. So, you have already got one equation from u, velocity, isn't it? So, you just put the value of u here and solve and simplify this equation. So, the equation will be mu del by del y into whole into minus 1 by 2 mu del p by del x ty minus y square, whole bracket close. Okay. If you simplify this one, then you will be come out mu will be mu into minus 1 by 2 mu del p by del x t minus 2y. Okay, you will get this equation. If you further simplify this equation, then ultimately your shear stress will be tau equal to minus half del p by del x t minus 2y. Okay. So you have got ultimately shear stress equation as minus half del P by del x T minus 2y. So to find out shear stress distribution, what you have to do? We have to consider two boundary equation. Okay, y equal to 0 and y equal to t by 2. So we will get maximum shear stress if u value will be 0, isn't it? Check it. If put in place of y, just put 0, then you will get shear stress equal to minus half del V by del x T, isn't it? So it will be maximum shear stress. Okay, and I will let you know where this maximum shear stress occur between two parallel plates. Again, minimum shear stress will occur if y equal to t by 2. Put the value of y equal to t by 2 in this equation. So if you put y equal to t by 2, your shear stress will be 0. That means the minimum shear stress will be 0 if y equal to t by 2, isn't it? So you have got two conditions of shear stress. One is maximum shear stress and another is minimum shear stress. Okay. So in the next slide, I am going to show you how this shear stress is distributed. How the diagrams look like. Up to this, everything is clear. If you have any doubt, you can ask me. Okay, so I think everything is clear about this shear stress distribution. Let's move to the next slide and I will show you how this shear stress distribution diagram can be drawn from this equation. Okay. Yes, this diagram. I think I have discussed about velocity distribution diagram already, isn't it? So this is the velocity distribution diagram and this is the shear stress distribution diagram between the two parallel plates. Here you can see the minimum velocity occurs. That means this in the middle of the plate. Okay, that means if y equal to t by 2, this here is the minimum shear stress occur. That means shear stress will be 0 here. Okay, and it will be maximum near the boundaries if y equal to 0, then your shear stress will be 0. shear stress will be maximum. That means it will occur near the two solid parallel fixed boundaries. Okay, so in the middle of the plate the minimum shear stress occur, and gradually it goes on increasing to the boundary. Okay, so this is how the shear stress is distributed if a flow is laminar and if the flow is flowing through two parallel plates. Is that clear? Yes, this is the I am marking this diagram. You can see this is the occurrence of maximum shear stress, both sides of the wall. In between the two parallel plates, shear stress is minimum. That means 0. No shear stress occur in between the plates. That means in the middle of the plate there is no shear stress. Okay, so let's move to the next topic. So I think in this topic we have discussed about 4 basic criterias. We have derived equations for 4 different parameters. Okay, so let me move to the next topic. And that is viscous flow, that means laminar flow through a circular pipe. That is called Hazen-Poiseuille's equation. We have to find out Hazen-Poiseuille's equation. We will get an equation which is known as we'll get a theory which is known as Hazen-Poiseuille's equation. Okay, so let's discuss about laminar flow through circular pipe. Let me check who are attending these classes. Yes. Can you see the figure? Here we have to find out laminar flow through circular pipe. So in this diagram, for moving further, we have to consider 2 basic assumptions. We have to assume 2 basic assumptions, and these are: one is we have to consider the flow is the flow which is flowing that satisfy Newton's law of viscosity, and the second one is there is no slip near the boundaries. Okay, so these are the 2 conditions we have to remember.